Material Physics 4. Today we're going to be talking about moment of inertia. So what is a moment of inertia? It is how much a body resists torque, resists being turned. So if we think about mass, mass is how much a body resists being accelerated in a straight line. So something's very heavy, lots of mass, it's difficult to accelerate. And if you put F equals ma, force is mass times acceleration, therefore something's got more mass, harder to accelerate. Okay? Moment of inertia is if we apply a turning force, something with a higher moment of inertia will turn less. So for a given torque, higher moment of inertia, lower turning, lower spinning, etc., etc. Now what's interesting about moment of inertia is it is not just dependent on mass. Consider this metal bar. If I turn it in the middle, you'll see it turns extremely easily. A small amount of torque, turning force, gives us a lot of angular velocity. Where if I hold it by the end, it's just so much more force to spin the bar. It's a real effort. You can try this at home. Much, much easier to spin it here than here. So the mass of this bar hasn't changed, but depending on where we spin it from, it takes a different amount of turning force to spin, therefore the moment of inertia has changed. And this should tell us the moment of inertia is not just dependent on mass. Okay, let's look at this bar here. And let us consider a particle on the bar. And the bar is spinning this way around a fulcrum here. So it's just a bar spinning. Let us consider this. Let us imagine the angular momentum of a particle here. Well, that angular momentum is going to go up if the particle has more mass, if the particle is further away from the fulcrum, which we refer to as R, or if it's travelling faster. So they'd all make sense, wouldn't they? If this particle was heavier, further away from the fulcrum, or moving faster, we'd expect it to have more angular momentum. We'd expect it to hurt more if it bopped you in the head. Easy. But we can do some neat little things here, because we know for anything spinning, the speed is equal to omega. Well, omega, of course, we know is the radial velocity, how much angle it's sweeping out in a given second, so how quickly it's turning. So we can sub that into here, and that gives us L equals mr squared omega. And then what we can do is we can take this bit and say, well, we're going to say that this is I, and that is our moment of inertia. That's the thing that's resisting the force. So therefore we can just write L is moment of inertia omega. And if we can count up to normal momentum, where P equals mv, so normal momentum is mass times velocity, angular momentum is moment of inertia times radial velocity. So we've got a very similar thing here. So that's for one particle. Okay? So therefore if we were to sum all the particles in the bar, what we'd have to write is the sum of all the angular momentums is equal to the sum of all the moments of inertia of all the individual particles multiplied by the sum of how fast they are all moving. So you could work out particle by particle by particle. But that's obviously a complete faff. So how could we get there easier? Well, it all depends on how many degrees of freedom our thing is spinning in. Okay? So we just got a sphere, and it's completely full of matter. It's actually a very, very simple equation. Our moment of inertia is just going to be equal to the radius squared of the sphere times the mass, because it turns out that it all balances out brilliantly, because the further out ones cancel out the ones closer, and so you just average it out to that. So that's easy. However, for most things that aren't spheres, it gets a bit harder. If they're just spinning in one plane, i.e. they're just spinning like this in one dimension, so they're nice and flat, just spinning like that, the moment of inertia is equal to k squared m, where k is just the difference from the fulcrum to the end. So again, fairly simple. However, if it's spinning in multiple dimensions, what you end up with is a moment of inertia that's a 3x3 matrix, like this, which is obviously much more complicated, but as you're moving on to degree physics, you'll see a lot more of this. There's a reason they taught it to you in maths. It wasn't to do maths at university, it was to do physics. So, this is, at a very fundamental level, what moment of inertia is. It's how much a body resists torque. It's dependent on both the mass and the distance from the fulcrum, and in fact, because it's mr squared, we can see it's got a much greater distance dependency than mass dependency, which would make sense. It would mean this bar is 4 times harder to turn like this than to turn like this, and that feels about right, if I'm honest. And we've got to do this horrible summing thing, and sometimes it's a 3x3 matrix, depending on what's happening. So there you go. There's another lesson later in the week. I'll see you then.